Okay, so this paper is basically for my own students, for my own class in college algebra, about solving rational equations and then some I stuff, imaginary number stuff at the bottom. But for the most part, it's solving rational equations and a little bit of I. Okay, so we have to remember when you're solving rational equations that the whole deal is trying to get your one fraction on the left side equal to one fraction on the right side, so that you can cross multiply and solve for x. So here I'm going to change my 2 to have a denominator, so multiply the top and bottom by 2 over 2, so that I'm going to have rather a 4 over 2, and I'll have the same denominators. So I have x over 3 equals x minus 4 over 2. So now that I have one fraction on the left and one fraction on the right, I can solve by cross multiplying. So 2x equals 3 times x minus 4. So we distribute into here. 2x equals 3x minus 12. And solving for x, I'm going to bring my 2x over. That's 1x. I'm going to add my 12, so x equals 12. Okay, we can always go back and check. 12 divided by 3 is 4. 4 equals 6 minus 2, sure does. So x equals 12 is the correct answer. Nothing to be done about it. Okay, so the whole point is getting one fraction on the left side and one fraction on the right side. So I'm going to run through these other ones kind of quickly because they're all basically the same. So multiplying this by 6 over 6. X over 5 equals x plus 6 over 6. Okay, once again cross multiplying. 6x equals 5x plus 30. So x equals 30. So 30 divided by 5 is 6. 6 equals 5 plus 1. Yes, it does. So 30 is the right answer. Okay, even here I'm going to multiply so that I have the same denominators. 60 minus x over 3 needs to equal x over 2. So 120 minus 2x equals 3x when you cross multiply. Add the 2x to both sides. And dividing, I believe this is 24, so x equals 24. And once again, you can check. Here's a 12. 20 minus 8, well, that's 12. Okay, so pretty easy when you have them set up like this. Get your two fractions combined into one, and then cross multiply. So same thing here, only now I have a little bit more to do. I'll multiply this one by 2 over 2, and this one by 5 over 5, so that I have a like denominator of 10. So 2x minus 5 equals x over 6. Cross multiply and solve. So let's see, 2x equals 30, so x is 15. Okay, so no problem. 15 divides 6, not prettily, but that's okay. 3 minus a half is 15 sixths. Sounds good to me. Okay, now this one we're going to do a little bit differently. Notice how we have a 3 and a 4 and a 6 and a 3. Well, we're still going to have to get the same denominators. So we multiply this one by 4 over 4 and this one by 3x over 3x. So we have a common denominator of 12x. And on the top we have 8, I believe, 8 plus 3x. Over here, I'm just going to multiply this by 2 over 2. So I have an 11 minus 2 over 6x. Now we could, of course, cross multiply. Sorry, 2x and 2x means 2x. We could cross multiply and divide, but then we're going to end up with some quadratics and some x squareds in there, and it might get a little bit ugly. So instead, I'm going to do something that is always true. I'm going to make this denominator the same as that denominator. So I'm going to multiply the right side here by 2 over 2 so that I have a denominator of 12x. Because a truth in all of fractions says if your denominators are the same, then your numerators must also be the same. Okay, of course, when you cross multiply, they just divide out nicely. So we really basically only have to deal with the numerators. So 8 plus 3x needs to equal 22 minus 4x when I distribute, of course, my 2 into this side. Okay, knowing this principle that if the denominators are the same, the numerators must be also, usually simplifies the algebra that you have to do. So we'll add this to this side and get a 7x. We'll subtract this from this side and get a 14. So x equals 2. Okay, we could solve this, of course, by cross multiplying. You do get some x squareds and an x, and you have to divide by a number with an x. But this principle usually simplifies things a lot. When you make your denominators the same, the numerators must also be the same. Okay, in fact, we're going to use that here on this next problem as well. So I notice this has an 18x, and this one we're going to make an 18x. So multiply this by 9 over 9. Multiply this by 2x over 2x. So on the left we have a denominator of 18x. And 9 times 5 is 45 minus 16x in your numerator. Now over here I need to multiply this by x over x and this one by 6 over 6. So I once again have a denominator of 18x. And x minus 6 is in your numerator. So this one you should be able to notice right away. Here we have an 18x and there we have an 18x. Your denominators are the same, so your numerators must therefore also must be the same. So 45 minus 16x needs to equal x minus 6. Okay, a lot simpler algebra here than if you were to cross multiply and get 18x squareds and whatever 18 times 6 is. You get larger numbers. So this principle helps you simplify your math a little bit. So bringing the 16x over, I will add this to this side, equals 51. So x is 3. Okay, so notice when we plug it back in here, 5/6. We don't have a problem with any denominators, so x equals 3 must be the correct answer. Okay, your calculator can once again tell you if that's true or not. Okay, number 7. Notice we have two denominators here that happen to be the same, so I'm going to bring this whole entire denominator over to that side by subtracting it. So 2 over x minus 2 minus x over x minus 2 will equal negative 2. So I have my denominators are the same, so I can subtract my numerators. 2 minus x over x minus 2 equals negative 2. Okay, over 1, of course, if we want to make this into a fraction, so that we can cross multiply and solve. So I'm going to come up here. Let me erase some stuff that we've already done. Make it larger. So I'm going to work this problem up here just for space. 2 minus x when we cross multiply equals negative 2 times x minus 2. So 2 minus x equals negative 2x plus 4. Let's add the 2x to this side, making it a positive x. We'll subtract the 2, making it x equals 2. Okay, now notice I put a cloud around here because look what happens. If I plug my 2 into this denominator, I get a 2 minus 2, which is a 0. I have an undefined fraction in my answer. Okay, we notice we can't have anything undefined, so the real answer is that this problem has no solution. As it's set up, if x equals 2, which is the solution, or is the answer, goes back into your denominators and it cancels stuff out and you get a 0 denominator, your actual answer is no solution.
So if we don't enter it in, do all that, it's wrong?
If you don't plug it back in and check your answer to make sure it's actually a valid answer, then you're probably not going to get full credit. Okay? You did the algebra correctly, but then you haven't synthesized your answer or analyzed the answer as you wish. Okay? So there might be one of those, but I highly doubt it. Okay, moving on. Let's see, what shall we do here? Notice we have a 2x minus 2 denominator. Maybe we could apply this principle up here also to this. So how to do, let's move the 1/2 over to this side, so we'll subtract the 1/2. Okay, there are lots of ways to do this. This is just one way. So now if I want to combine these denominators, I'll multiply the top and bottom by x minus 1. I'll multiply this one by 2. And I have a 3 left over, so 3 over 2x minus 2 equals 2 times 2 is 4 minus and x minus 1. And I have one denominator of 2x minus 2. So once again, my denominators are the exact same, therefore my numerators must be equal also. So 4 minus x plus 1, okay, minus x minus a minus is a plus. 3 equals 5 minus x. Bringing this over here, minus 2 equals minus x, so x equals 2. Okay, this denominator equal numerator kind of thing really helps us simplify our math, because when these are the same, these must be the same. Okay, it can simplify your algebra considerably once in a while. So our last one of this family, I'm going to bring my 2x plus 6 over to here, because I notice x plus 3 and 2x plus 6 are kind of similar-ish. The x minus 2, not so much. There could be lots of things you could do, cross-multiplying and such, and it would just get really ugly. So let's just do this and make it simple. So 3 over x plus 3 minus 5 over 2x plus 6 will equal 1 over x minus 2. So if I want to make these two denominators the same, I simply have to multiply this one by 2. That will give me the 2x plus 6 that I desire. And on the top I have a 6 minus 5, which is just 1. And over here I have a 1 over x minus 2. Now our convenient principle also applies here. If your numerators are the exact same value, that means that the denominators must be the exact same value. Okay, because 1 over something needs to equal 1 over that same something. So this will simplify our stuff considerably. So x has to be negative 8. So this is a negative 10 over here and a negative 10 over there. So 1 over negative 10 needs to equal 1 over negative 10. And of course it does. Okay, so there's some rational things. Making one fraction on the left equaling one fraction on the right. Okay, cross multiplying if you can't make the denominators the same. When the denominators are the same, the numerators must be equal, and it saves yourself a lot of algebra headache. Now, our imaginary numbers. So we need solutions. We can't take a negative 40 radical in your calculator, but we can take it in your brain, in your imagination. So this is what we do. We separate 40 into the product of two numbers, one of which is a perfect square. Let me make this a little bit bigger so you can see it. Okay, so the negative stays on the outside because it's on the outside. Negative 4 square roots to 2i. Okay, the I from the negative, the square root of 4 is 2. And the 10 stays underneath the radical because it's not a perfect square. And that is your term, negative root of negative 40 in terms of I. So our answer has an I in it. That's what that means. Okay, there's a couple ways to do this one. Let's simplify root 12 first. That's negative 4 times 3. Root 20 is negative 4 times 5. Okay, so whenever we're trying to simplify radicals, we're looking for perfect square multipliers. So negative 4 times 3, 4 is a perfect square. So this square roots to 2i. This square roots to 2i also. And now we multiply like terms. 2i times 2i is 4i squared. 3 times 5 is 15. But you should remember, we can't leave things with an I squared in it. So instead of I squared, we multiply by negative 1. So our final answer is negative 4 roots of 15. Okay, because I squared gets replaced with negative 1. 4 times negative 1 is negative 4. Let's see if that's better. Okay, so whenever we're taking the square root of a negative, we get an imaginary value. So root negative 9 is 3i, root 25 is 5, so 3i times 5 is 15i. Purely imaginary number. Okay, here's 9i, square root of negative 81. Here is 8i, the square root of negative 64. That's 72i squared, but we never leave an I squared. We always replace it with negative 1. So our answer is negative 72, just the number negative 72. Okay, the real number negative 72. And then lastly, some operations with I. Here we are adding, so we're combining like terms. 6 plus negative 4 is positive 2. 2i plus negative 3i, in other words, 2 minus 3 is negative 1i, and you never have to write a 1 in front of a variable or a letter. So 2 minus i is that one. Here we have 3 minus 2. 3 minus 2 is just 1. Negative 5 minus a negative I. Minus a minus is a plus. So negative 5 plus 1 is minus 4i. Okay, remember to distribute the negative. Minus a minus is a plus. So here's multiplication. We do it just like we do binomials. 6 times negative 4 is negative 24. 6 times minus 3i is minus 18i. 2i times minus 4 is minus 8i. And 2i times minus 3i is minus 6i squared. So we combine our like terms in here. That's minus 26 i's. We replace I squared with negative 1. So negative 6 times negative 1 is actually a positive 6. So negative 4 plus 6 is minus 18. So our negative 24 plus 6 is negative 18. The number part always comes before the imaginary part, even if they're both negative. And now our I stuff. So here's our I cycle. I'm going to do this in large up here because you need to know your I cycle. So I'm going to erase all this stuff just to give myself some room. Our I cycle. Like a bicycle. No, just kidding. I cycle. So I to the first power is just, of course, I. I to the second power is negative 1. I to the third power is negative I. And I to the fourth power is positive 1. Those are the only 4 values you're ever going to get. I, negative 1, negative I, or positive 1. Okay, and they're cyclical. So I to the 5th is the same thing as I to the 1st, or just I. I to the 6th is negative 1. Because it goes in order. It cycles through. So back to our problems and see if we can make sense of this. I squared, well, that's just negative 1. So that's pretty easy. I to the third is just negative I. That's pretty easy. I to the 41st, though, means how many times have we gone through this cycle and where are we now? So because there are only 4 choices, we divide the power by 4. And that we know is 10 with a remainder of 1. So we have gone through this I cycle 10 times, and we are back to I to the first power. So I to the 41st is the same thing as I to the regular first, which is just I. Okay, that'd be the same value. So our last problem, here we have negative 2I raised to the 5th power. So here we're going to distribute this 5th power to both of our terms. Negative 2 to the 5th times I to the 5th. Negative 2 to the 5th power is negative 32. I to the 5th power is the same thing as I to the first power. So our simplified version is negative 32I. And hopefully that has made you smarter. We'll see you on your test. Okay, bye.